Okay, hello operating systems. Here we're going to be moving on and looking at some more in xv6. The motivation is to just get into the code a bit more, practice with it, and we'll start with what the hardware has for us, what it gives us. And so I put a couple notes here of what the hardware gives us. These are a few things that we will really get into the nitty-gritty details soon enough, but this is a high-level overview. So one thing that the hardware, in our case we're looking at the x86 CPU architecture. So this does memory address translation. Okay, so what that means is when I'm in my C code, the memory addresses that I see in my C code are not the actual physical memory address of the physical memory itself. And we're going to look at an example here. I have a version of xv6 where I added a few things. I'm going to run this in Emacs so I can save my history easier. Okay, I've booted up. I have a memory program called memory. Okay. I forgot that was like that. So the xv6 isn't actually, the shell there isn't actually catching the control C. So I'm going to kill my whole thing. All right. Let's try this again. So I'm going to run this like this with the ampersand so it detaches. All right. And let's look at the code for this memory.c. All right, here's memory.c. So it prints some different types of memory. First is main. So if you just have a function name with no parenthesis, then what C does is it puts in the address where that instruction is in memory. So where does the function main start? Where's the code for it? Then we have a global variable. So the address of this global variable up here, I have a global variable. It doesn't mean anything. It's just a global variable. So that's at this address, B78. I have a parameter, an argument here. argc is a parameter to main. That is stored in the program's stack. And the address for argc is here. And then I have a string that I get some memory for using malloc, and then print the address of that string. This %p is pointer. It's basically the same as %x here. All right, so there I have the different memory addresses. So main, the code for main starts at address 0. The code for the global variable starts there, and so on. And if we look in our xv6 documentation, this is page 31, eventually in the part that's chapter about memory. This is showing what the memory looks like to my process. So the operating system is making it look like to my memory.c program that starting at address 0 is user text. That means the program itself, the code for the program. So looks like that's true here, that the address of my main function is down there low. Okay, next higher up is user data. That's typically global variables. And there's my global variable at B78 at a low memory address. Then we have the stack, which is the part of memory that's used for keeping local variables and arguments to functions, keeping track of function calls and local variables. And so there I have my local variable argc, which is just above the global variable in terms of the memory address. And then this part here, everything, the heap, which is more data. So when we ask for more data, then it goes above all of this stuff. And we see that there. Okay. You might want to take a pause and just kind of absorb this picture. One of the things I want to show with this example is proof that these can't be the actual real memory addresses. The documentation says that that the addresses that we see here are called virtual. That's not, so the xv6 documentation says those are not the real addresses that are actually going to physical memory, but it's the operating system making it look that way to us. In xv6 you can do Control P. It gives a list of processes. I modified mine a little bit so it gives a little more information, but we see there's a process 4, PID 4, that's my memory program, so I'm going to kill that. And if I do my Control P again, there it is. Now what I'm going to do is run a bunch of different copies of memory. All right. So you'll notice that they all have the same memory addresses. And if this was a physical memory address, you would hope that different copies of the program would have different memory. If there are separate copies, right? I start one. Generally speaking, you want separate copies of the same program to have their own memory. But we see the same memory addresses. And if I took any of my other programs, if I took my primes program and I printed out the address of argc, the address of main, then it would have the same values there as well. The reason is because each process gets its own view, so each process thinks that it's the only thing that's running. That's the way the operating system makes it look. So all of this stuff here looks the same for every process. Yep. And so one of the punchlines is that this all works because the CPU architecture itself has this in mind. Okay, so there's physical stuff in the hardware that does this translation for us. And that's going to be in the second chapter here where we see how this actually works. Basically, there's something in hardware that when it sees this memory address, it's going to automatically translate that into some other address. And it'll be specific for each process. So each time a process starts running, one of the things that has to happen is the memory translation stuff has to be set correctly for this process. In here, let's see. Let's start some important stuff. When a context switch happens, when a new process runs. Okay, so if we're going to switch which program is running in the CPU, then what do we need to do? So definitely we need to load up the CPU registers for that process, right? When a process stops, you save the state of the CPU. So save state of the CPU for old process, and then we load CPU registers for the new process that we're going to put in. And we also need to do the memory translation. There's going to be like a lookup table. That's part of what we have to do anytime we're switching processes. Okay, and we'll get into that soon enough. I just want to give you a sneak peek. All right, so that was one part of the hardware. By the way, in QEMU, if you do Control-AX, that kills it. So Control-AX is a good one to remember, and Control-P. All right, so memory address translation, and we'll see that. So another thing that's important that the hardware gives us that makes everything work the way we want to is the concept of an interrupt or a trap, or those are two words that often mean the same thing. So an interrupt is something that happens either in our code or in hardware that should really be taken care of by the operating system. Okay, so this could be device I/O. The hard drive is sending data. If the hard drive is sending data into memory, then the CPU should take care of that, or sorry, the operating system should take care of that. Operating system's supposed to be in control. All right, maybe it's a timer interrupt, and it's time for one program to pause while another program runs. The operating system should be in charge of that. Or it could be a system call. So the operating system has this interface where it's supposed to be in control of the file system. If you want to do something to the file system, you want to make a system call. Okay, the hardware itself, the x86 architecture, has this built in. So it has built in that the first program that runs when the computer boots gets to decide what happens. So you can think of this as a lookup table in, let's see, we'll go over to our slides. So what must be in the operating system? We already had a list of processes, a list of file descriptors. Okay, hardware it must provide, context switch, let's say interrupt, trap, handlers. So there must be a way to specify. So there has to be some kind of instruction where we can say, hey, use this address, this code over here when XYZ interrupt occurs, right? Okay, and whoever is in charge when the computer boots basically gets to do this. And so what we can think of is that there's some part of memory where there's interrupt, let's see, different types of interrupts. So let's say that we have the timer interrupt. Go to memory address 0x1234, and then you'd have hard drive interrupt, go to memory address 0x, something like this. All right, syscall interrupt, go to memory address okay? And all right, that's that. So I have a demonstration over here that the operating system xv6 is in charge. That when things happen that the operating system should be in charge of, xv6 is there, and I'm going to just give this one here. So when you have a problem in the program, when you divide by 0 or you have a segmentation fault, the operating system gets to decide what happens. And I want to just give a demonstration of that. I have a program here, fault.c. So it expects one argument that's going to be 0, 1, or 2. And if it's a 1, then this program is going to do a segmentation fault. Right? It's going to try and access memory that it shouldn't. And what that looks like, so if the argument is 1, which is 1, so this is what I'm going to do. So I have a bad pointer, which is this value. And if this is the truth of the world here, this kern base is where the operating system code is. Remember, this is virtual memory address, this, because it's all anything that we ever see in our program in terms of pointers is actually virtual memory pointers, which you can safely ignore when you're writing C code normally, when you're not doing operating system code. All right, this kern base is defined to be this 8, this thing, right? 8 with 3 zeros and then with 4 zeros. So that's the start of the operating system code. So that means that if I try to set that as the address for a pointer and then take the value, I should not be allowed to do that, because that's where the operating system lives, and regular programs shouldn't be able to look inside the operating system memory. That would be bad if you let regular programs do that. All right, so if that works, then I'm going to print what the value is. All right, which would be a bad thing. I went and looked at that address in the operating system. Maybe it's some sensitive information about passwords or something. All right, so then I'll print it. If they give a 2, then I'm going to do a divide by 0 error. I have a variable 0 here that's just 0. And then I go ahead and divide it. Okay, so let's go back to my run this, and my program there is called fault. So my when I was supposed to do a segmentation fault or a memory fault of some kind, it says fault trap 14. And notice that I did not get to this print statement because it killed the process. I'm claiming that this is in the xv6 code where this is happening. We'll look at that in just a second. So let me try the other one, divide by 0. That one also has a similar statement there. And it also did not get to the next line in the code. All right, so now let me Control AX to stop QEMU. And then I want to look for, where does this print statement happen? So if I look through, this looks here like kind of what I was looking at. So I want to look in trap.c. Okay, so this statement here, and if I want to be certain that this is actually what's happening, then I could, I don't know, change this slightly. Capital T. Here's my capital T. That's just a demonstration that when this thing happened that the operating system should really be in control of, the operating system is indeed in control here. So what happens is when the system booted, you set up some, divide by 0. Something like that. All right. This is part of initializing the system, and in that initialization of the system, this trap function, so the address wherever this trap function is loaded inside the operating system, that is what got set to handle divide by zeros and these other things. I mean, segmentation fault as well. Okay, cool. Locks. Okay, it's going to be a little bit longer before we start taking a look at locks, but to do a lot of things that we want to do, not just in operating systems, but anytime we have a computer where multiple different things are supposed to be running at the same time, we can get into problems if we do not have atomic instructions like test and set. I'm going to show you an example for that as well. I have a program add.c here. Let's just look at the code. So this expects 2 arguments, a file name and then an integer, and what it's going to do is it's going to read a binary raw number out of there, out of the first 4 bytes, and then increment it by n. So let me just go ahead and do that. I'll do that down here. Okay, I'm going to do add num.txt, say 10. All right, and it told me that the final value was 10. It started at 0 and then incremented 10 times. So let's do add num.txt 5. It was already 10, now it increased by 5. All right, and the way this happens is, let's look at it up here. So we have the file name. I'm going to do 5 times or 10 times, depending on the parameter. Open the file. Let's say the file was opened. If the file was opened, I'm going to read a size of count is an integer, so I'm going to read 4 bytes into this integer. So that would be in count. If there's no problem with the reading, close the file, increase count. Now I'm going to open the file for writing and write out the result. So I should have read the file, increased by 1, wrote out the result. And then I have this inside of a loop, so it's going to happen some number of times. Okay. Let's start off again and say that we want to put 50 in there. So it got up to 50. Now the interesting thing is if we try to run multiple of these at the same time. Okay, so I'm going to do add num.txt 100. I'm going to detach that so I can run another one. Okay, so they're detached and they both finished. One of them ended up with a final value of 166, and one of them ended up with a final value of 174. Let's do it one more time. Let's just add a 1. Okay, so the first one to finish thought there was 174 in there, and the second one to finish thought there was 166. The value should have been 200. And the reason for this is because we're reading here, then incrementing, and then writing, and we really want that all to kind of be one atomic operation if this is going to work out correctly. Let's go over to our slides just to show. So we'll call this why we need locks. And I believe the O-step operating system in 3 pieces has a nice example like this as well, but we'll do it again here as well. So let's say we have process 1, process 2, executing. So each one of them is going to do a, let's see, we have count, read count, count plus plus, write count. Okay, and then we'll have over here this is fancy here, right? So the value of count in the file. All right, so let's say that it was initially before any of the processes ran, there was a value in the file that had, let's just say 1 or 0. I'm going to need some more room, so we'll call this 12. All right. So if we read count, so we'll read 0 there, count plus plus, then we're going to write out 1, and so then the value of count in the file changes from 0 to 1. All right, now let's suppose that process 2 is going to read count. And what value does it read? It reads 1. And then it's going to do count plus plus. And then it's going to write count. Okay, so let's say count plus plus, it's going to be 2. This is good, but what happens if process 2 gets stopped and process 1 gets a turn again? So while we're in here, the value of count that's in the file doesn't change until there's a write. So if I read count here, let's say that this process got interrupted, it hasn't done its write yet, then I'm going to read 1. And let's say I do my count plus plus, so now I have 2, and then I write count, and I'm writing 2. So now the value in the file has changed to 2. And then let's say it's process 2's turn again, write the value of count that process 2 has. It has the value 2 there still. Okay, so how many writes did we do, or how many plus pluses? We had 1, 2, 3, but we only have a value of 2 in the file. Okay, the reason that we have a problem is because we can get this stuff here where we read, we increment, and we write. If it all happens in chunks, right? If they all happen together without being broken, without being stopped and interrupted, then it works, it's good. But if we don't, if we get stopped in the middle, then there's potentially a problem. All right, this is going to happen in our operating system where we have multiple different processes that are supposed to be running at the same time. We'll have issues like this as well, just to keep track of things in the operating system. So something that we need from the hardware is atomic operations. So for example, if we had an atomic increment operation, that might be useful for this scenario. When we get into the operating system, we'll have we'll see what the atomic operations are that the hardware gives us that lets us avoid these issues. Okay, so I'm gonna, let's see. Okay, I think what we're going to do, if you want, you can pause and look at that file. Maybe you paused. I want to say something quickly about adding programs to the xv6. So I have done this before, but I'll show you again. So I have this add.c. I can #include .h files that are in xv6, so different ones of these potentially are useful for different needs. Then I'm basically writing a C program, except all I have available to me is things that are in this directory. There is an A to I function in that's part of user.h. It's included from there. There is a printf function, but it requires a file descriptor, one for std out. There's a read function, so that's what we have access to. There's an exit function. It does not take a return value. Normally you would have exit 0 with a return value of 0. This one in xv6 doesn't take a return value. All right, so I can make a file like this, add.c. If I want it to be part of the operating system, I need to go to my makefile. And I have, so these are the programs that I've added at this point to my xv6. I've got primes, and so I'm just going to go through and do whatever I did for primes. So uprogs _primes, that gets linked in somewhere in the makefile, so you need to do that. Listing the .c files here, that's going to make it get compiled, primes.c, all of those, and that's it. Okay, so the makefile does the rest of the magic, so that as long as you include your program in those two places, then when you build your xv6, those programs will be, so I see here this primes, there was add, memory, and fault. So those are all files, compiled files that are in my program. Control AX. All right, so what I'm going to do now is just go through and comment those programs, just as if you want some extra me talking. If you don't want that and you want to look yourself, I believe all of these are readable by you. You can go and view them here. Okay, but I'm going to go and just put some comments in like we're supposed to. Okay, so the purpose of this file, this is if the program fault, see what happens. The OS should get control and kill the process. Okay, so we've got our command line arguments. So standard checking of argc and usage statement. Then we have our standard grabbing command line arguments. All right, some stuff. So I'm printing here so I can see on the screen how far we got. That's why that print is there. If they gave 0, then there's supposed to be no fault. If there was a 1, then this is supposed to be a bad. Supposed to be a bad memory access because in xv6 kernel code starts at virtual memory address bad B. That's why I picked that. Okay, and if the process is killed, we shouldn't see this line. All right, this is supposed to be a divide by 0, and I tried first having like this, but the compiler caught that as a problem. So I put a variable with the value 0, and the compiler didn't catch that because it's not set to catch everything. As long as the program is killed, we shouldn't see this printout. Okay, and if there was a fault, we shouldn't see this either. And we should only see this if we didn't choose 1 or 2. And I'll note there are other problems we could try to make happen. And some of these are defined in traps.h. So these are predefined values in the x86 of things that might happen. One of them we got was a 6, and one of them we got was a 14. So 14 was our bad memory, and 6 was divide by 0. We got a 6 instead of a 0, so I don't know. But so these are some other things that might happen that we could try to make happen. All right, that is this program. If you want to pause the screen, go ahead. And we'll go on to add.c. So this is supposed to be a demonstration that read, inc, write doesn't give the right answer if multiple programs doing it at once, and the read, inc, write isn't atomic. Okay, atomic means happens all or nothing. And we use a file for this, all right, because that's a way we have that multiple programs can access the same data right now. Okay, so we have our standard argc check and usage statement. Then we're going to have our standard grabbing command line arguments. We're expecting the file name and then an integer. Then we're going to repeat a number of times. Read, inc, and write. Okay, and this looks longer than it really is because I'm actually checking return values. Okay, so I'm opening the file. If it doesn't open, then probably this is the first time we've run this. We're actually starting it at 0. Okay, if we're able to open the file, then we read the count. So this was probably first time, no file yet. here is file yet read count. Right, checking the status again, and then we have our increase the count, whether it's coming from the file or initialized to 0, and then we write it out. And that's it for this one. So one thing to be careful of was I need to make sure to close the file because I'm going to be repeatedly reading, increasing, writing, and each time I want to close the file to make sure that I see this behavior of strangeness. Okay, that's add. Let's take a look at memory. So this was seeing what memory addresses get printed for different types of things. All right, so this is a global variable that's in the text or data section of memory, according to a picture like this. Different places will call it the whole either text or data there. All right. So when we do this thing here, this is going to print the memory address where the main function is. And that should be in text or data, right? Depending on here, they're, I believe, using text to refer to the program and data to refer to globals. Okay. Then we have a local / argument. Local variables and arguments to functions get stored in the same, should be on the stack. And the stack is an actual stack that builds up. So here's the stack, and when you declare local variables or call a function, those things just get put on top of the stack and then popped off when you're done with them. If you don't know that, go look it up. All right, and this should be on the heap. All right, so that's not a stack variable, it's supposed to go higher. And I didn't say what this does, so we'll leave it. Here, sleep forever, so that we can have program running in the background, if so desired. All right, if we wanted that. If we don't want that, then we can comment this out. All right, I think that's good enough. So you've had some more looking at xv6. Let me see. Yep, we'll say that's it for now. The end.